Hey guys, so in this video I wanted to show you how to read the sensor data off this IMU sensor by STM Electronics. So it is the LSM6DSOX IMU, and I'll be using I2C to read the data off the sensor. So in this tutorial we'll cover the C program to read the data off the sensor, a little bit about the protocol I2C, and we'll also walk through the data sheet so that we understand what's happening. And in different parts of the tutorial, I'll hook up my Logic Analyzer so that we can view the data on the scope and understand what data we are sending to the IMU and also what we're reading back. And lastly, all the code will be posted on GitHub, and that link will be in the description. So as you can see on my screen, we are reading the X, Y, and Z of the gyroscope data right here, and then also the X, Y, and Z of the accelerometer data. And then in the background, we can see the I2C protocol reading the raw data from the sensor. So let's get started. Here I have the datasheet open for the sensor, and basically what the sensor lets you do is measure the acceleration in the X, Y, and Z direction, and then it also lets you measure angular rate in the pitch, roll, and yaw directions from the gyroscope. So the first thing you'll want to do is open a new window from VS Code, and if you haven't installed the Raspberry Pi Pico extension, please do that. I have a video that actually explains how to do that on Linux using Ubuntu. So we'll want to create a new C++ project. Let's name this IMU I2C. Pico 2 is fine. Let's pick a location. As far as features, we'll want to use the I2C interface, and then also STDIO support. We'll be using console over USB. Everything else we can leave as is, and then we can press create. Now let's open up the C file, and as you can see, it has some boilerplate code in it. Let's delete this, and I'll walk you through the code to read sensor data off the IMU. So the first thing you'll want to do is include some libraries. So first we have stdio, which is the standard library. So for example, we have printf is in here. And also we have the pico/stdlib library. So this contains basic functions for setting up the GPIO pins and also setting up the Pi to be able to use printf to print to the serial terminal using USB. And then lastly, we have the hardware/I2C library, which will contain all the functions for setting up I2C and also reading and writing to the sensor. So next, let's determine which pins on the Raspberry Pi Pico 1 or 2 we want to use for I2C. So for I2C, it is all the blue labeling on this diagram. And as you can see, there's I2C 0, and then there's also I2C 1. So that means that the Pico has 2 different I2C cores. So in this tutorial, let's just say we'll use I2C on GPIO pin 9 and 8. So GPIO pin 9 is the serial clock, and GPIO pin 8 is the serial data. So let's add that to our program. So in line 5, I have the I2C core 0 instance definition, or instance. And then I have defined the 2 pins that are for serial data and serial clock. So the next thing we'll want to do is write the function that initializes or enables us to use I2C on the Raspberry Pi. So for that, I have this function called I2C core init, and it takes in the I2C instance, which would be core 0, and then it also takes in the 2 pins, so serial data and serial clock. The first function here is used to initialize the I2C hardware block, and it takes in the instance argument. It sets the clock to 40 kilohertz. So as you can see in the data sheet here, the maximum clock frequency for I2C is 400 kilohertz. And Well, actually, you can use, it looks like 1,000 kilohertz, so a million, but let's just use 400 kilohertz for this tutorial. So the next thing we want to do is set the function for the two GPIO pins we selected. So if we look at the diagram, instead of using pin 12 and 11 as GPIO pins, we want to set their function to I2C. So that's what these two functions are doing right here. And this GPIO pin func I2C enum is part of the Pico standard library. And lastly, we need to set the state of the GPIO pins for I2C. So what this does is it pulls up the pins, so that means they'll be high initially. As we can see in this little diagram for I2C, before the transaction begins, serial data and serial clock are both high, or they're both 1. And then during the transaction, you can see that they're toggling and data, the clock's toggling and data is being transferred and sampled by the clock. And then at the end of the transaction, which isn't shown here, both clock is high, as you can see, but the data will also be high. I also wanted to add that all of these functions are a part of the Pico library. So the I2C function is part of the hardware I2C library, and then the GPIO functions are part of the Pico stdlib library. So the next thing we'll want to do is determine the slave address for the sensor. So as you can see, the slave address is this right here, but then there's an X. So this X can either be a 1 or a 0, and that's dependent on whether these pins or this pin is high or low. So if it's 1, then the X will be a 1 right here, and if the pin is 0 or grounded, then there will be a 0 right here. So this table gives a better explanation. So here's like the part of the I2C address that doesn't change, and then whether this pin is high or low, then we'll get a 0 or a 1. And just through experiment, by leaving the pin floating, it defaults to this address right here, which is 6A. So let's add that to our code as well. So usually for constructing the address for the I2C transaction, you have to append a read-write bit to the end of the address as seen right here. But when using the Raspberry Pi Pico I2C like read-write functions, you don't have to append this bit, it'll automatically do it for you. So that's kind of nice. So just to add in hex, this is 6A. So the way I2C works is kind of shown in this table below. It's not the best diagram, but I'll explain it. So let's look at this first table 11. So first, the master will send a start transaction, and then we'll transmit the slave address with the write bit. So the write bit will be 0, as you can see right here. And then we'll wait for the slave to respond with an acknowledge because its address matches what we sent. And then we'll send the sub address. So this is just the register. So this could be like a configuration register or something. So some register that we want to write to. And then the slave, and then the slave will send another acknowledge, and then the master will send the data that we're writing to this register, and then the slave will send an acknowledge that that data was written, and then the master will send a stop transaction. So as you can see, between each sort of transaction between the slave and the master, the slave will send an acknowledge transaction to let the master know that its transaction was successfully sent to the slave. When writing multiple bytes to a slave, it's very similar. So the beginning's the same, except we do multiple data and acknowledge like transactions. And then we have the start bit or stop condition. Okay, so let's look at the read transaction next for reading 1 byte from the slave. So first the master sends the start condition, and then it sends the slave address along with a write. and then we wait for the slave to send back an acknowledge, and then the master writes the register that we want to read from to the slave, and then the slave sends an acknowledge, and then the master sends a restart condition, and then the master sends the slave address again with the read byte. So now inside the IMU, there's like some register that is pointing to all of the other registers inside the IMU, and by writing this to the IMU, that register inside the IMU is now pointing to whatever data is contained at this register. So now we can start reading that data from this register. Hopefully that makes sense. And also, before each sort of read-write transaction, we have to send the slave address again. So we send it right here because we're writing, and then we send it right here because we're reading. So so we send the restart, then we send the slave address with a read bit, then the slave sends an acknowledge bit with the data, and then the master sends a no master acknowledge. It's basically like terminating the transaction, and then the master sends a stop bit. Reading multiple bytes of data from the slave is very similar as reading a single byte, except this data and then master acknowledge, data, master acknowledge kind of repeats several times, and then the ending is the same as above. So we'll see this in the logic analyzer as well, and hopefully it'll make better sense once you see that. Okay, now let's write the function to send data or write data to the sensor. So that'll look like this. So this reg write function is a wrapper function around the Pico's own I2C function, which is from the hardware/I2C library. So let's go through this entire function real quick. So it takes in the I2C instance, which will be core 0, and then it'll take in the address, which will be the device address of 6A, and then it takes in a register value. So we haven't looked at the registers yet, but there will be registers that we need to read from or write to. So in this case, we'll be writing to them with this function. And then it takes a pointer to the buffer that will contain the data that we want to write to the register location. And then it takes in the number of bytes that we want to transmit or write to the IMU. So the first thing we have are two variable declarations. So we have number of bytes, which will basically give us the number of bytes we've written to the IMU. And then we also have a message array, which will contain the register value and also the data that we are sending. So first we check that the number of bytes we want to send is at least 1. So if it's less than 1, we'll return 0 and exit the function. Next, we are constructing the message that contains both the register value and the data that we want to write. So as you can see, element 0 will contain the register value, and then I+1 contains the data. Next, we use the Raspberry Pi Pico function I2C Write blocking, and this takes in a few parameters, as you can see in the notes above. So it takes in the I2C instance, which will be core 0 for us, and then it takes in the address of the device, which we defined right here. Then it takes in the message as a pointer, so we defined it as an array, so just by passing in the name of the array itself is a pointer, and this contains the address at the start and then also all the data that we want to write to. And then next it contains the length of the data in bytes to send. And lastly, there's a parameter we passed in for no stop. So we set this to false because at the end of each write, we want to end the transaction, and then when we do another write, we want to start with the start bit for I2C. So this function will return the number of bytes we wrote to the sensor, and then we exit out. So the next thing we'll want to do is write the reg read function. So that'll look like this right here. So the input parameters for this function are very similar, or they're actually identical to the write function. As I said before, it takes in the I2C instance, the address of the device, the register we want to read from, the buffer that will contain the read data from this register, and also the number of bytes we want to read in case we want to do a burst read. So first we have a num bytes read, which will contain the number of bytes read from the sensor. And then also we have this little check right here that'll make sure that we're at least reading one register or more. And if we're not, we'll return 0 and then exit the function. Actual reading begins right here, and it starts with the write. So the reason why it starts with the write is because we need to point inside the device, inside the IMU device, we need to make sure we point to the register we want to read from, and then we can start reading the data from that register. So what this does, this is the same function as up here, but with some slight differences in the parameters we're passing in. So it takes in the I2C instance, it takes in the address we want to read from, but now remember this write is so that we can point to it. And then it takes in the register, the number of bytes we are writing, which is 1, so it'll only be the register value. And then also this is set to true so that we start the next transaction with a restart rather than a start. And this will let us seamlessly begin a read transaction right after a write transaction. So now this I2C read blocking function is also from the hardware I2C library. And this takes in the I2C instance, the address, the buffer that will contain, or actually a pointer to the buffer that will contain the data that was read from the address that was set right here. And then the number of bytes you want to read in case you want to do a burst read. And then we set no stop to false so that we end the transaction. And then when we do a next transaction, it'll start with a start bit rather than a restart. And then lastly, we return the number of bytes read from the IMU. The next thing we'll want to do is look at the register map and determine what registers we need to set up in order to power on the IMU and read data. There's a lot you can do with the sensor, but we're interested in how can we just get the basic functionality working, which is getting accelerometer and gyroscope data out of the IMU. Just through a quick scroll of this list, a very important register that I see off the bat is this Who Am I register, and this contains a fixed value of, let's see here, this is 6C, and this is a good register to have because if we can read back this register from this address, so 0F, that means our read function that we implemented right here is working. Next, we need to consider 3 control registers, so that'll be control 1 XL, and then control 2G, and then also control 3C. And if we can write to this address, and if we can write and configure these 3 registers, and then also read back the same data that we wrote to those registers, that'll confirm that our write function is working correctly. So let's add the IMU init function and let's go through it line by line. And we also need to add our register defines right here. So Who Am I is at address 0F, and then we have the 3 control registers, which are 10, 11, and 12 in hex. So 10, 11, and 12. Another thing you can see from this diagram is that the Who Am I register is read only, and then the config registers are read-write, so R for read and then W for write. So to start, we initialize an array with 1 element, and we also have this number of bytes, which will contain the number of bytes read from each register. You could also include a number of bytes written to, and then set that equal to this function, the reg write, and then it'll allow you to do some better error handling, but let's leave that out for now and just make it a little simple. So these first two lines read the value at the Who Am I register. So it takes in the I2C port, which is core 0, takes in the device address, which is 6A. It takes in the Who Am I address, which is 0F. It takes in the buffer, which will contain the read data from this address, and then also the number of bytes we want to read, so that'll be 1 byte. So when we execute this, we'll print out, or at least we should print out, this value right here, which is 6C. The next register we'll want to consider is the accelerometer control register, and this lets us do some basic configuration for the accelerometer. And if we scroll down a little bit, we see the layout of the register, and the first bit is 0, and then the other bits map to these tables on this page. So for the first field, the accelerometer high resolution select, we'll leave it at its default and output from the first stage digital filter. And then for the full scale, we can come down to this table down here. And what we're selecting is the range of accelerometer measurements we want to read. So this goes from negative to positive 2 g-forces all the way to plus or minus 8 g-forces. So 1 g is basically equal to the Earth's gravitational force, which is 9.8 meters per second squared. So for this tutorial, let's select plus or minus 8. So then we'll have 1, 1 right here. So 1 and then 1. And then for the ODR, which stands for output data rate, we'll select how fast we can read from the sensor. So initially the sensor is powered down, and then as soon as we write one of these values to this register, it'll be powered on. So let's say we want to read the sensor at 1 kilohertz, so that means we need to set the output data rate at 1.66 kilohertz. So that'll be 1000, and that'll be right here. So 1000. So in these 4 lines of code, we are going to write those values to the control 1 Excel register. And those values are right here, which maps to this right here. So first we'll write to that register, and then we'll read back the data from that register and then print it out. And those two should match. However, I'm printing it out in hex, and this is represented in binary. So the next register we want to consider is the gyroscope control register. This has a very similar setup as the accelerometer. So the first bit is 0, and then the next bit is the, UI chain full scale. So let's leave this as default. The next 2 bits are the full scale. So remember, the gyroscope allows you to measure rotational speed, so degrees per second. So let's say we want to pick plus or minus 1000 degrees per second. So that means we'll select 1, 0. So we'll have a 1 here and a 0 here. Next, we need to pick the gyroscope's output data rate. Normally it's powered off, but let's say just like the accelerometer, we want to read at 1 kilohertz, so that means we need to pick 1.66 kilohertz. So then it'll be 1110, which will be right here, 1110. And as you can see in the code, we have exactly what we stated expressed in binary. So first we'll write to the control 2G register with the data, and then we'll read back that value at the control 2G register, and then we'll print it out. And what was read from should be the same as what we wrote to that register. Lastly, we have this control 3C register, and the only thing we need to consider here is set this IF inc to 1, and this will allow us to do burst reads, so multiple byte access with serial interface, so either with I2C or SPI. So as you can see right here, we only have a 1 right here. So if the reset is 0, The reserve bit is 0, the IF inked is 1, as you can see right here, and then the rest of the bits will leave at 0, or their default value, which is 0. Lastly, this function returns a number of bytes read. This you don't really need. This could actually just be a void function because I'm not really doing any error handling in this function, but I'm just going to leave it as is, and you can add to it later. So the next thing we'll want to do is add our main function, and this contains stdio init ol, and this allows us to print to the serial terminal using printf. Next, we'll call our I2C core init function, and this just initializes the I2C to a clock frequency and also sets up the 2 GPIO pins, so pin 8 and 9, to use their I2C functionality. Next, we call our IMU init function, which is this one up here, and this does a bunch of register reads and writes to configure the IMU. Next, we have our while loop, and then we're sleeping for 4 milliseconds. So a good thing to do is to just loop this IMU init function in here, and if we can continuously read the who am I register and then also do these read writes, that means our reg read and our reg write function is working properly. All right, so now let's connect everything to our breadboard. So let's put the Pico on. Let's put our sensor on. So let's connect our ground first, so pin 38 on the Pico to ground pin on the sensor. This might be a little hard to see, but this pin is labeled as 39, so the one right below it is ground, and then we have ground right here. Next, let's connect pin 36 on the Pico to VIN on the sensor. So pin 36 is right here, and then VIN is this guy right here. So that's here. Now let's connect pin 11, which is our serial data on the Pico, to the serial data on the actual sensor, which is right here. So fortunately, this breadboard has labels right here. So pin 11 is this, and then we'll connect that to SDA right here. And then lastly, we have the serial clock, which is on pin 12, and that'll connect right here on the sensor, so serial clock. So pin 12 on the Pico all the way to serial clock on the sensor. And that's all. For I2C requires the clock and data connections, and also we need to provide power and ground for the sensor. So before we flash our program onto the Raspberry Pi Pico, let's come over here and compile it to make sure we have no errors. And let's open up another terminal, and then let's CD into our build folder and then list everything. And the file that we are interested in is this UF2 right here. So this is what we're going to flash onto the Raspberry Pi Pico, and it'll start running this program we have written. So in order to flash the program onto the Raspberry Pi Pico, we need to mount it to our computer. So the first thing you'll need to do is hold down this boot select button, and then you'll plug in your micro USB, and then once it's plugged in, we'll let go. And then if we look at my screen, we can see that the Pico has mounted as a drive on the computer. Next, we can go back to our terminal and then CP for copy, and we'll want to copy this UF2 file to media, and then the username, and then the name of the drive. And then when we press enter, we see that the drive goes away or demounts, and now the Pico is running our program. So next, let's bring up a terminal, And let's use Minicom. So Minicom is a tool that allows us to stream data to the serial terminal. So if you don't have it installed yet, so please install it with sudo apt install Minicom. Type in your password. I already have it installed, so it's clear. So in order to view the data stream on the serial terminal coming from your Raspberry Pi Pico, let's type in minicom-d. Let's select the device, so it'll be dev/tty ACM0, and then -b, let's select the baud rate, so the baud rate will be 115200. Press enter. So I got a permission denied error, and what we need to do is add sudo right in front. And now we can see the print statements that we set in our code in this IMU init function be print or sent to the serial terminal on our computer. All right, so now we are printing the data that we read from the sensor to our serial terminal using Minicom. And below I've captured a single transaction of each of the I2C transactions for what we've written in this function over here. So this first bit is where we are reading the who am I register. So the first thing we do is write the device address to the slave, and we get this acknowledge bit, and then we write the address for the who am I register, which is 0f. And then we get another acknowledge bit, and then we start a read transaction. So we send we send the device address for the IMU once more time, which is 6A, and then we read back the value at 6F, which is 6C, or sorry, at 0F, which is 6C. Next, we have the transaction for the control 1 XL register. So first we have to send the device address again. We get it acknowledged, then we send the address or the register address, and then we write that value to this register. And then, so that's the write transaction for I2C. And then for a read transaction, we send the device address, we send the address we want to read from, and then we begin our read over here. So then we send the device address again, and then we read back the value at this address, which is 8C. And we can also see that in the serial terminal. And the same thing is true for our write and reads to control 1G and control 3C. So we can see that we wrote 88 and we're reading back 88, and we can also see that in the serial terminal. And then, so that is for the control 2G register right here. And then for the control 3C register, we wrote 4 to it, and then we're reading back 4, and we can also see that in the serial terminal. So the next thing we'll want to do is go back to our register map and find the registers that contain the gyroscope and accelerometer data. So if we scroll back, we see this out X and then LG, and then we see X and then Y's and Z's for the G, and both H for high and L for low, low, high, and then also for the accelerometer, so that's for the gyroscope, X, Y, and Z, and then for the accelerometer X, Y, and Z, we have the 6 right here as well. So let's go to the description of the out XLG register in the datasheet. So by reading this description, we see that the pitch x-axis angular rate is expressed as a 16-bit word in 2's complement. So basically what they're saying is that one part of this 16-bit word, or the LSB, is contained in this register with the L for the x-axis, and then the MSB part of the 16-bit word is contained in the next register right here with the H, so the high and lower for the x-axis. So what we need to do is we need to combine these together into a 16-bit int value in our code. So now let's take a look at that. So in our code, I've added the register that contains the x-axis lower byte, and we only need this register because we're going to burst read through all the other registers. So just to quickly explain that, let's go back to our register map. So I've only added this register right here, which is at address 22, and then in our code, or when we do an I2C transaction, we're going to burst read address 22 all the way down to 2D in one I2C transaction. I've also added some variables to hold the raw data that we get from the gyroscope, and then the 16-bit 2's complement integer that we'll create with the raw data for the gyroscope and accelerometer. And then after that, I have float arrays that will contain the actual physical unit value of the gyroscope and the accelerometer data. So that'll be in, the gyroscope will be in degrees per second, and then the accelerometer will be in g-forces. So what this function does is it performs an I2C burst read starting at address 22, and then it increments up from there up to 12 bytes. So each output data from all the registers will be put into this IMU raw buffer. So here we can print out the raw values just to see them, and we'll look at that in a sec. So let me comment all this out, and let me comment this in, and let's look at the raw values being printed to the serial terminal, and also let's look at them on the logic analyzer. And let's also call this inside of our loop, and then let's move the IMU init function outside of our loop, because we only need to call that once. So let's come over here and compile, and then let's go back to our bash terminal and reflash our board. So what you can see now is the raw data from the gyroscope and accelerometer being printed to the serial terminal, and then also we have it shown on our logic analyzer. So if I do a single shot and then unplug the Pico so we stop printing, we see that this transaction right here is printed at this line right here, which is pretty cool. So first we send the device address, we get an acknowledgement, and then we write the address in which we want to read from, and then we issue another write to the device, and this is the beginning of our read. So you can see WR is write and then RD is read, and then we begin our burst read from address 22 all the way to address, I think it was 2D in our datasheet. So it was printing pretty slow because I made this sleep 1 second so that we could look at the data and compare the data being sent on the logic analyzer and make sure it matches the data that's being printed. So let me comment this out. So the next thing we'll want to do is create the 16-bit 2's complement integer. So that's done with this piece of code. And so the first raw buffer, for example, in this line 117, the first element in this array contains outXLG data. And then the data contained in this other element, so the next element above, contains the higher 8-bit data for the X angular rate. So what we do is OR the lower bit with the upper bit shifted up by 8, which then creates that 16-bit integer. And then we store it into our gyro raw array, which is an int16 type. We do this for each X, Y, and Z for the gyroscope, and also the X, Y, and Z for the accelerometer. So now that we have the data in a 16-bit 2's complement integer, we need to convert this into a physical unit for both the gyroscope, which will be degrees per second, and also the accelerometer, which will be in g-forces. So the unit of the raw data coming out of the IMU is this unit called an LSB. And what we need to do is multiply it by some factor, whose units is for the gyroscope is milladegrees per second per LSB. So as you can see, for the angular rate or gyroscope, the full scale that we selected was plus or minus 1000 degrees per second. So our multiplier will be 35, and its units is milladegrees per second over LSB. So that's what we're doing right here. We're multiplying the LSB times this unit, which gives us, so the LSBs both cancel out, and then we're left with milli-LSBs. And then to get degrees per second, we divide by 1000, which will cancel out the mil right here, and then we're left with degrees per second. So that's that same calculation applies for the X, Y, and Z for the gyroscope. And similarly, for the accelerometer, we configured it to have a full scale of plus or minus 8, and the multiplier that we're going to use to convert it into a physical unit is this 0.244, whose units are millig's per LSB. So just like the gyroscope, the raw data for the accelerometer is LSB, and then when we multiply it by this constant, whose units are right here, we're left with millig's. So the LSBs cancel out, and we're left with millig's. And then to get rid of the milli, we divide by 1000, and now we're left with g's. And as you can see, 1 g is equal to 9.8 meters per second squared. So the same calculation applies for the accelerometer X, Y, and Z. And then now we have the true reading of the accelerometer and gyroscope data, and we can print that to our serial console. So let's compile. Well, actually, let's let's change this to, let's say, 4 milliseconds. Let's recompile, reflash our board. Okay, so here we go. We have the gyroscope data on our left and the accelerometer data on our right. So you can see that the gyroscope data is basically 0, which makes sense because we're not rotating the IMU at all. And then for the accelerometer, the X is 0, the Y is 0, and you can see that the Z is about 1 because there's one force of gravity coming down on the sensor, which makes sense. So for the gyroscope, if you look on the board, you can see the printed axes on here. So if we want to create a positive rotation along the x-axis, X is pointing in this direction. So using the right-hand rule, rotating the board in this direction will generate a positive angular rate. So let's look at this column right here. And if we rotate it this way, we get a positive angular rate, and then rotate the other way, we get a negative angular rate. Also, we see the Y right here is pointed in this direction. So rotating the board this way will give us a positive angular rate, and the other way will give us a negative. So if we rotate it this way, we see that we get a positive angular rate right here in this middle column. And then when we rotate it the other way, we get a negative angular rate. And then the Z is coming up this way. So when we rotate the board in this direction, so counterclockwise, we'll get a positive angular rate, and then clockwise, we'll get a negative angular rate. So counterclockwise, we get the positive angular rate. Let me do that one more time. And then other way, we get a negative angular rate. And then for the accelerometer, if we shake it in the X direction, we can see the X go up and down in acceleration, but the Z pretty much stays at 0. Or sorry, the Y basically stays at 0, and the Z stays at 1. And then if we shake it in the Y direction, we should see basically the opposite, where the X stays at 0, Y will kind of like go up and down, and then the Z will stay at 1. And then for the Z, same thing, if we go up and down. Another thing you can do is you can apply Earth's gravitational force on different axes. So right now it's on the Z, and then if we point the X up to 90 degrees, now Earth's gravitational force is seen on the X, and the Y and the Z are basically 0, and then same thing for the Y axis. If it's 90 degrees, then the Y is almost 1, and then the X and the Z are basically 0. And that's pretty much it. I'll make another video where we can measure exact angles. So if I hold it at 45 degrees, we'll be able to print 45 degrees to the serial terminal, which is pretty cool. So stay tuned for that. Feel free to leave comments if you have any questions, and thank you for watching. And don't forget to subscribe so that we can grow this channel. I would appreciate that very much. All right, so see you later. Bye.